The next question, FeH2O6 plus. The compound is given FeH2O6 6 time with overall charge of the complex is 3 plus, is strongly paramagnetic, whereas FeCN6 3 minus, right? 3 minus is weakly paramagnetic. We just discussed in the part 1 video regarding the VB theory. What is the meaning of strongly paramagnetic? Dear students, paramagnetism for a complex is generated by the presence of unpaired electron. Strongly paramagnetic means it having lot of unpaired electrons. So we can say more unpaired electrons are there if it is strongly para. So weakly para in the sense less number of unpaired electrons. Let's observe the same thing. You know, H2O. H2O in the common cases, they act as which one? A weak field ligand, but cyanide is a strong ligand. So you got the answer, but still we can explain through the concept. Dear all, step number 1, we have to write the ground state electronic configuration of the central metal atom. Your central metal atom is which one? Iron. You know, iron atomic number is 26, so we can write it as 4s2 3d6. That is the configuration. What is the oxidation state of iron in this question? Dear all, the oxidation state of iron, X. Water is aqua is a neutral ligand and overall charge of the complex is +3. So X is equal to +3. So here iron is in 3 plus oxidation state. You know, 3 plus mean you have to remove 3 electrons. So 2 electron let me remove from 4s, 1 electron from 3d. So remaining is 3d5 and 4s 0. Okay, let me just fill the 5 electron. 1, 2, 3, 4, 5 and 4s is vacant. Step number 3, let us check it dear all. What type of ligand is given? Water. Water in common cases, they act as a weak field ligand. Weak field ligand. So weak field ligand means no pairing happen, right? No pairing happen. What you have in the previous step, the same thing. So total how many unpaired electrons are there? 1, 2, 3, 4, 5. 5 unpaired electrons are there. Alright, 5 unpaired electrons are there. Let's see what about in this case. Dear student, here I'm not writing step number 1. Again, the same thing. Step number 1, write the ground state of this metal atom. Metal atom is iron itself. So the same thing you will get it. What is oxidation state of iron? That is step number 2. Step number 2 is the excited state. Iron oxidation state is X. 6 cyanide charge is -6. Overall charge is -3. X is equal to +3. Here also I think we got +3, right? So step number 1, step number 2, both are same like previous case. So I'm just repeating. Step number 2, the configuration. We having 3d5 and 4s0. All right. Then step number 3, let us check our ligand. There is a change in ligand. The ligand is cyanide. Dear students, cyanide is a strong field ligand. It's a strong ligand. If there is a strong ligand, we have studied that electrons undergo pairing. So we can draw like this, the d orbital electrons, how they will pair. This first electron, pair it. These 2 electron, pair it. This 1 electron, stay there. Is it paramagnetic? Yeah, it's paramagnetic because it contains 1 unpaired electron. But is it strong paramagnetic? No. In the first compound contain total 5 unpaired electron. Here just 1 unpaired electron. As the number of unpaired electron increases, paramagnetic character increases. So that is the answer. Now, explain CONH363 plus. So we have a complex cobalt NH3 6 time with the overall charge 3 plus is an inner orbital complex, whereas NiH2O 6 time 2 plus is an outer orbital complex. Dear all, inner orbital complex and outer orbital complex. We know octahedral complexes. Octahedral geometry we can determine through 2 hybridization. One is called sp3d2 or d2sp3. Both are the octahedral geometry. So sp3d2 and d2sp3, what is the difference? You can see in the d2sp3 hybridization, they are taking the inner d orbital for the hybridization. Therefore, they are called inner orbital complex. Inner orbital complexes are also known as low spin complexes. Okay, if the hybridization is D2sp3, they are using inner d orbital, therefore they are called inner orbital complexes or low spin complexes. At the same time, in sp3d2, they are considering the outermost d orbital, therefore they are called outer orbital complexes. Outer orbital complexes are also known as what? High spin complexes. High spin complexes. Okay. Outer orbital complexes are also known as high spin complexes. We can go to the question. Here we have to prove that it's an inner orbital and outer orbital complexes. First one. The complex step number 1 as usual by the VB theory. Central metal atom is cobalt, atomic number 27, right? So 27 means we can write the configuration is 4s2 3d7. Step number 2 is the excited state. What is oxidation state of cobalt in this question? Cobalt X, amine is a neutral ligand, overall charge is +3, so X is +3. So cobalt is in 3+ oxidation state. 3+ mean we have to remove 3 electron, right? So let us remove 2 electron from here, 1 electron from here, remaining 3d6, 4s0. So 6 electrons are there in d orbital. 4s orbital is free. Step number 3, we have to check the presence of ligand. Here the ligand is ammonia, amine. Amine is a strong ligand. If there is a strong ligand, we know electrons undergo pairing, right? So let us make the paired condition here all. What happens after pairing? These 2 electron already paired, these 2 electron pairing, and these 2 electron paired. All right. Now we have to check total how many ligands are present in the system. Total there are 6 ammonia, right? Amine ligands are there. So you have to provide 6 vacant orbital in the metal atom. At present you have 1, 2, 3 orbital. So this is the 3d orbital and 4s orbital. After 4s what you have? 4p orbital. So I need total 6 orbital to make or to occupy 6 ammonia. So 1, 2, 3, 4, 5, 6. All these 6 orbital, when you club it or making the hybridization, this is 2d orbital, d2. This is s, this is 3p, d2sp3. As I told you, d2sp3 mean they're taking inner d orbital for the hybridization. Therefore, they are called inner orbital complexes. I also told you that inner orbital complexes are also known as what? Low spin complexes. Second question. What about second? The complex is given nickel H2O. Okay, step number 1. Write the ground state electronic configuration of the metal atom nickel. Nickel atomic number 28. We can write 4s2 3d8. Step number 2. Step number 2, what is the oxidation state of nickel? Nickel X, water is a neutral ligand and overall charge is +2. So nickel is in +2 oxidation state. +2 mean you have to remove outermost 2 electron, remaining 3d8, 4s0. So 3d8 electron, let me fill like this. 1, 2, 3, 4, 5, 6, 7, 8 and s is 0. Step number 3, identify the ligand given. Here the ligand is water, aqua. Aqua is a neutral ligand. So pairing won't happen. Let me take the previous situation once again. Alright, 8 electron. S is there. This is 3D. This is 4s. And you have after that 4p orbital. Right, after 4s the orbitals are which one? 4p. If you want D, that also you can take it. 4D also there. Okay, this is 4p and this is 4D. Dear student, here pairing not happen. Therefore, it's paramagnetic. And total you have to occupy 6 water ligand, right? 6 aqua ligand. So you have to provide 6 vacant site. So where is the vacant site? 6 vacant site. This 1, 2, 3, 4, 5, 6. So dear all of you, let us mix those orbital. S orbital, 3p orbital and 2d orbital, sp3d2. See all of you, sp3d2 means octahedral geometry where they are taking outer d orbital. Therefore, this is called what? Outer orbital complexes. What is the other name or outermost? the outer orbital complexes, we will call it as what? High spin complexes. Okay, that also keep in mind. Maybe the same question they can ask in another way. Show that this complex is a low spin complex, this one is an outer orbital or high spin complex. Okay, so low spin complexes are inner orbital complex, and outer orbital complexes are high spin complexes. Inner orbital are low spin, outer orbital are high spin complexes. Predict the number of unpaired electrons in the square planar complex. The complex is given PT. Platinum is the central atom with a CN4 with a charge 2-. Alright. Dear all, we have the method how to find out the geometry, everything. VB theory. Step number 1, write the ground state electronic configuration of platinum. Ground state electronic configuration of platinum. Platinum atomic number is 78. Dear student, platinum, we have to know the electronic configuration. The last 2 orbital is enough. It is around 6s1 5d9. Just remember, all of you, platinum atomic number 78, its configuration outermost 2 orbital is 6s1 5d9. Step number 2, we have to find out the excited state. What is excited state? The oxidation state. Platinum atomic number X, we don't know. Cyanide charge is -4, overall charge is -2 for the complex, so X is equal to +2. So here platinum is in +2 oxidation state, right? +2 oxidation. So +2 in the sense it has to lose 2 electron from the outermost. So from 6s orbital 1 electron, from 5d9 1 electron, so remaining is 5d8 and 6s 0. Now step number 3, identify the ligand which is given. Here 5d8, how we can write 5d8 electron? 1, 2, 3, 4, 5, 6, 7, 8. Here, third step is identification of the ligand, right? Ligand is cyanide. You know, cyanide is a strong ligand. If there is a strong ligand, electrons undergo pairing, right? Electrons undergo pairing. These 3 set of electrons are already paired, and these 2 electrons pair up, right? Paired. All right. So the total, how many? This is 5d, 6s, then we have 6p. Dear all of you, total how many ligands are there in the system? Total 4 ligands are there. So you have to provide 4 vacant orbital. So this is 1, 2, 3, 4. What is the hybridization? This is a d orbital, s orbital, and 2p orbital. dsp2. Yes, dsp2 means structure is square planar. That's correct one. But the question, how many unpaired electrons are there? Dear student, unpaired electron we are calculating in the final step, step number 3. In step number 3, can you see any unpaired electron? See, all electrons are paired. Why? Because there is a strong ligand. So because of the presence of strong ligand, all electrons are paired. So the answer is what? 0 unpaired electron. Okay, no unpaired electron in the system. Next question. What is meant by unidentate, didentate or ambidentate ligands? You know the common principle. What is meant by a unidentate or a monodentate ligand? The ligands which having only one donor atom. The ligand which having only one donor atom through which it can make a single bond with the metal atom or a coordinated bond with the metal atom is called a unidentate or monodentate ligand. So what is meant by a bidentate or didentate ligand? It's a ligand having 2 donor atom. It's having 2 donor atom and it can make 2 sigma bond at a time with the metal atom. And what is meant by ambidentate ligand? Let us see the example for what are the example for unidentate ligand we studied. Lot of example we studied. Amine, NH3, H2O, aqua, and the chlorine, bromine, right? All halogens are belongs to which one? The monodentate ligand. So many other OH minus hydroxide, NO3, nitrate, sulfate, the nitrate, all are belongs to which one? Unidentate ligand, which having only one donor atom. If you consider NH3, nitrogen can make a bond with the metal atom because nitrogen contain electron. H2O, oxygen can make a bond with the metal atom. Chlorine can make. So this is called a unidentate ligand or a monodentate ligand. What is meant by didentate ligand? Didentate, or we can call it as bidentate ligand, right? Didentate in the sense the ligand which contain two donor atom. The two example which we discussed in this chapter, one is called oxalate, one is called ethylene diamine. You know what is oxalate? Oxalate means COO minus, COO minus, or we will call it as C2O4 2 minus. See, by using this oxygen, the negative charge, oxygen, this negative charge, it can make a bond with a metal atom. See, there are two donor atoms. That's called a bidentate ligand. En, what is En? Ethylene, you know, ethylene CH2, CH2. Diamines means NH2, NH2. This is called ethylene diamine. By using nitrogen, this lone pair, it can make a bond with a metal atom. By using this lone pair, another metal bond, like sigma bond, coordinated bond. See, so this is called bidentate ligand. What is a special type is called ambidentate ligand. Dear student, ambidentate ligands are certain monodentate ligand. Ambidentate ligands are certain monodentate ligand. So ambidentate ligands are actually monodentate ligand. It having actually two donor atom, but at a time it can use only one. See the example we studied, SCN. What is SCN? Is called thiocyanate. Either the metal can make a bond with sulfur in SCN, or we can write NCS. What is NCS? Is called isothiocyanate. So here same formula, but you see here metal connected through sulfur, metal connected through nitrogen. Similarly, cyanide and isocyanate, CN and NC. They are actually monodentate ligand because at a time it can make only one sigma bond, but actually it contains two sites, right? And another example we studied that NO2. Metal can make a bond through nitrogen, or metal can make a bond through oxygen, ONO. See NO2 and ONO. Either nitrogen or oxygen. If it is NO2, we will call nitrito-N because it's connected through nitrogen. Here nitrito-O because it is connected through oxygen, right? So these are actually monodentate ligand, but at a time it can make only one sigma bond. So what is ambidentate ligand? Ambidentate ligands are certain monodentate ligand having two sites actually, but at a time it can make only one sigma bond with the metal atom, right? Next one. Specify the oxidation number of the metal in the following coordination complex. Let's do this fast, all of you. What is the oxidation number of cobalt in this question? Cobalt oxidation state, we have to calculate X. Water, aqua is a neutral ligand. So one cyanide charge is -1. En is a neutral ligand. Overall charge of the complex is +2. Therefore, X is equal to -1 come to the right side. It becomes +3, right? X is equal to +3. Next one. Cobalt oxidation state X, 2 bromine charge is -2, En is a neutral ligand, overall charge of the complex is +1. So here also X is equal to +3, right? +3. Here platinum oxidation state X, 4 chlorine charge is -4, overall charge of the complex is -2, therefore X is equal to +2. Correct? X is equal to +2. Now, here Fe, 3 potassium outside, you know 1 potassium charge is +1, so 3 potassium +3, Fe oxidation state X, 6 cyanide charge is -6, overall it's a neutral compound, 0, therefore X is equal to +3. Here chromium oxidation state X, amine is a neutral ligand, 0, Cl, 3 chlorine charge is -3, overall it's a neutral compound, so 0, X is equal to +3. So if you know the charges of each of the ligand, very easy to calculate the oxidation state of the metal. Draw the figure to show the splitting of d orbital in an octahedral complex. Yes, student, according to the crystal field theory, CFT, we studied how the d orbital of the metal atom splitted in the presence of a ligand in an octahedral complex and tetrahedral complex. Here they are asking you octahedral complex. In an octahedral complex, you know, here we are actually considering the energy of the system, right? The energy of the levels, it's increasing. First, we will consider the free metal d orbital, the d orbital, the 5d orbital of the metal atom, correct? In the ground state. Now they entered into a average energy state, right? The same 5d orbital just to get excited into a average energy state. What are the d orbitals? You know very well. The 5d orbitals are dxy, dyz, dxz, dx square minus y square and dz square. These are the 5d orbitals we have. When a ligand approaches, dear all, what is crystal field theory says that? When a ligand approaches the metal atom, the metal d orbital splitted into two set of energy. If it is in a octahedral complex, they are splitted into two level in which the first three level dxy, dyz, dxz, dxy, dyz, dxz, which is going to the lower energy state. The next two orbital goes to the upper energy, a higher energy state, right, with a higher energy state. The last two orbital, which all are dx square minus y square and dz square orbital goes up. The below level or the three set of energy, this is called triply degenerate one, because they are having same energy orbitals are called degenerate orbital. These are three, right? So triply degenerate orbitals are called T2G. This level is called T2G. These three orbitals are called T2G level, and the upper two level is called EG level, T2G and EG level. And you know the average energy state, and what is the energy difference here? Here around 0.4 delta O. Here it is what? 0.6 delta O. That's the energy difference. What is meant by delta O? That is our crystal field splitting energy. Here you know T2G and EG. The difference between T2G and EG level, what is the energy difference, is called what? Delta O. For octahedral complex, delta O. It's crystal field splitting energy. So this is the diagram you have to write for this question. So when a octahedral complex undergoes splitting in the presence of a ligand, what happened? The 5d orbital splitted into two sets. Three orbitals below, they are called T2G, dxy, dyz, dxz orbital, and two orbitals on the top, which all are dx square minus y square and dz square orbital. Okay, so this is the way of splitting the d orbital in the presence of a ligand. One more thing. We studied there are two types of ligand. One is called strong field ligand. Someone is called weak field ligand. What is a strong ligand? If a strong ligand approaches the metal atom splitted with a large differences. The delta O will be very greater. That's the difference between a strong ligand and weak ligand. Okay, if there is a strong ligand approaches T2G and EG, the splitting will be very high. If it is a weak ligand, the delta O will be very small. Clear all of you? Next one. What is spectrochemical series? We discussed before. Spectrochemical series is compulsory to know the series of each ligands. Okay. Spectrochemical series means it's an arrangement of various ligands in the increasing order of their crystal field splitting energy. Dear all, you can see if it's starting from iodine to carbonyl, right? Iodine to carbonyl. Normally, we will consider H2O, including H2O and the left species, considered as a weak field ligand. Including water generally, including water and the left species means oxide, oxalate, hydroxide, fluorine, all these are considered as weak field ligand. After water, all of them considered as a strong field ligand. So the series is starting from weak field to strong field. For what? Crystal field splitting. As I told you, if a strong ligand approaches the metal atom, the splitting energy, the splitting difference is very high, right? T2G, EG are very high in difference. Same thing. So strong field ligand can make very strong splitting of the d orbital of the metal atom. If it is a weak ligand, small splitting. Okay, so that is spectrochemical series. How can we say the definition? It's a series of arrangement of various ligands in the increasing order of their crystal field splitting energy, crystal field splitting power. Okay, so weak field or strong field. Now, a solution of, the question is solution of NiH2O6 times. So NiH2O6 times 2 plus is the complex given. It's green in color, but a solution of NiCN4 2 minus is colorless. Dear student, it's very simple to do this kind of question. Everything is regarding VB theory. Again, let me take step number 1. Step number 1, write the ground state electronic configuration of the metal atom nickel. Nickel atomic number 28, therefore we can write the configuration is 4s2 3d8. What is the step number 2? Write the excited state of the metal atom. What is the oxidation state of nickel here? Nickel is X, aqua is neutral, overall charge is +2. So oxidation state is +2. Alright. +2 means remove 2 electron from the outermost orbital. So we have remaining 3d8 orbital, right? 1, 2, 3, 4, 5, 6, 7, 8. Alright. And you have 4s orbital here. This is 3d, this is 4s. Step number 3, identify which ligand is given. Your ligand is water. You know, water is a weak ligand. Aqua is a weak ligand. So no pairing happen. Just write the above step once again. No pairing. Okay. Filling of electron careful. 3d and 4s. Now dear all, here we not need to find the geometry of the molecule. Here the green in color. So how you can say that a complex can show color, the other one cannot? If the compound, you know, color of a coordination complex is mainly because of the excitation of electron from the ground state to excited state by absorbing the energy from the visible region. Any electrons cannot move or excited. Only the unpaired electrons can make a transition to make the compound color. So if the compound contain, what is the condition to make a color, dear all of you? The first condition, the complex should contain a unpaired electron, at least one unpaired electron. If the compound contain one unpaired electron, the unpaired electron can excited and it can show the color of the complex. Is it contain unpaired electron? Yes, because it's a weak ligand present, no pairing happen. If there is a unpaired electron, if it contain a unpaired electron, it can show a color. Okay, so the answer is ready. So let us prove that this complex is colorless, which means they doesn't contain unpaired electron. It's very clear because cyanide is the ligand. Cyanide is a strong ligand. It will make pairing of electrons. So of course there will not be anything. So let me just to go through as a descriptive examination. Step number 1, write the ground state of nickel. Same like the previous case, 4s2 3d8. Step number 2, write the excited state. Excited state is what? Nickel, I think here also in 2+ state. So 2+ mean remove this 2 electron. Remaining is 3d8. 1, 2, 3, 4, 5, 6, 7, 8. All right. Step number 3, dear all of you, it is cyanide is the ligand given here. Cyanide is a strong field ligand. If there is a strong ligand, electrons undergo pairing. So after pairing, what is the situation? These 3 set of electrons are already paired and these 2 electrons also get paired. So there is no unpaired electron. If there is no unpaired electron, it cannot show color. All right. Next one. What is mean by expecting question chelate effect? Give an example. Dear student, what are chelating ligands? We studied what are ambidentate ligand, right? Ambidentate ligands are certain monodentate ligand which can have 2 sites, but at a time they will use only one. We studied isothiocyanate, thiocyanate, nitrito, N-nitrito, etc. Here there's a special case is called what? The chelating ligand. Dear student, chelating ligands are certain, they are certain bidentate, or polydentate ligands. Which one? Chelating ligands are actually certain bidentate or polydentate ligand. They are actually bidentate or polydentate ligand which have an ability to make a ring structure with the metal atom. What's that? Chelating ligands are certain bidentate or polydentate ligand have an ability to make a ring structure, with the metal atom. They are called chelating ligand. This effect is called chelating effect. Let me show you one of the example. What are the example we studied for bidentate ligand? We studied En, oxalate, etc. Right. So dear student, I'm taking one of the metal here, suppose nickel. Any metal atom. Okay, general we can discuss. A metal atom. Let me take one oxalate here. What is oxalate? You know, COO minus, COO minus. This is one oxalate ion ligand. Another one COO minus and COO minus. See, this is a bidentate ligand. You know, by using this oxygen atom, it can make a coordinate bond with the metal atom because it's a bidentate ligand. 2 sigma bond can create at a time. So this is also. Can you see there is a ring structures are forming? Right. So when bidentate or polydentate ligand when connected to a metal atom, there is a chance to make ring structure. These kind of ligands are called chelating ligand. And one more thing all of you noted, a chelating ligand, if it is there, the stability of the complex increases. All of you just note the point very carefully. If there is a chelating ligand in your system, stability of the complex also increases. Okay, next one. Among the following, which is most stable complex? It's a special question, dear all of you. Very carefully listen. Among the following, the most stable complex is, dear students, stability of a complex is mainly depends on different factors. First factor we can consider, if the metal atom with a greater oxidation state in the complex, higher stability. If the metal atom in your complex is with a greater oxidation state, higher stability. Second factor, just we discussed now in the previous slide, if there is a chelating ligand, it can make stability. So let us see, in question number 1, all of you, if you calculate the oxidation state of species here, iron I am calculating, iron X acquires a neutral ligand, overall charge is 0. So here oxidation state is 0. What is oxidation state of iron here? Iron X, amine is a neutral ligand, overall charge is +3, so oxidation state is +3. In this case, iron X, oxalate, 1 oxalate charge is -2, 3 oxalate charge is -6, overall charge is -3, X is equal to +3. Next one, here iron X, 6 chlorine charge is -6, overall charge is -3, so X is equal to +3. See, in all these cases, and except the first one, iron is in +3 oxidation state. So the first factor, one of the highest factor determine the stability of a complex is the oxidation state of the metal atom. Greater the oxidation state of the metal, greater stability. But here all are +3, right? So that's not factor is possible here. Next factor, chelating effect. Yes, there is a chelating ligand or not? What is a chelating ligand? It's a bidentate or polydentate ligand. Just to check it, is there a bidentate or polydentate ligand? Water is a monodentate ligand, so it cannot make chelation. Amine is a monodentate ligand, it cannot make chelation. C2O4 is oxalated, dear student. Oxalate is a bidentate ligand, right? Yes, it can make chelation. Whereas Cl, chlorine, is also a monodentate ligand. So option third one is the correct answer. So dear all of you, if there is a chelating ligand in the complex, stability can be greater. Okay, keep in mind. Next one. What will be the correct order for the wavelength of absorption in the visible region for the following? A special question. I'm taking the complexes one by one. Ni, here all metals are same, right? Nickel, nickel, nickel. Here the ligand is NO2. What is NO2 ligand is called? Nitrito-N. Here the ligand is amine, right? NH3. Here the ligand is aqua, water, H2O. Question, what will be the correct order of the wavelength? Actually, we didn't discuss any question regarding wavelength in this chapter, right? But there is a connection with the wavelength. You have studied now crystal field stabilization energy or splitting energy. Crystal field splitting energy, as per the order, we arranged various ligand in the increasing order, that is called spectrochemical series, right? This is our spectrochemical series. From weak ligand to strong ligand, as based on what? Crystal field splitting energy. Weak ligand will make less splitting and strong ligand will make more splitting, correct? Okay, fine. Which all ligands we are discussing in the previous question, dear all of you? NO2, amine and water. Dear student, as per their energy order, crystal field splitting energy order, I can say the strongest one or highest crystal field splitting power is for NO2. NO2, after that ammonia and then water. Water is a weak ligand. Okay, just check it. NO2 greater strong ligand and then NH3, then H2O. Just check it. What is NO2? NO2, NH3, H2O. See, NO2 is the strongest, which one? The ligand, okay? So, NO2, NH3, H2O. This is the order actually in the increasing order of their crystal field splitting energy. So, greater, stronger one is NO2, weaker one is H2O. How we can connect this energy data into wavelength? Question is regarding the order of wavelength. You may studied in 11th grade, there is a chapter structure of atom. What is the relation between energy and the wavelength? E is equal to hc by lambda. E is equal to hc by lambda. So tell me, dear student, how energy related to wavelength? Energy is inversely proportional to wavelength. Correct. This is the increasing order of energy. So the question, what will be the correct order of the visible region in the following? They didn't ask increasing or decreasing. Okay. So this is the increasing order of energy. So what will be the increasing order of wavelength? Just opposite. Correct. This is for higher energy. For higher energy, lower will be the wavelength. So as per the wavelength order, we can write the opposite order. Weak ligand having greater wavelength, then NH3, then NO2. Hope you clear? Right, all of you? It's important. Okay. Next one. On the basis of, expecting question, on the basis of crystal field theory, which one? CFT. Write the electronic configuration for D4 configuration ion if delta O less than P. So here actually they have to specify which is system, right? Like whether octahedral or tetrahedral. Mostly they will ask you the question from, especially D4, mostly they will ask you for octahedral complexes. Dear all of you, in an octahedral complex, we studied how the d orbital are splitting. Right? So let me tell you the basic idea. Here the system is given D4 configuration, which means d orbital contain 4 electron. Okay. D4. So d orbital contain 4 electron. 1, 2, 3, 4. This is the D4 system. Okay. One more information they given here. Delta O is less than pairing energy. What is this? This is giving a very big idea about this question. What is the meaning of delta O? What is meant by delta O? It is the difference between T2G and EG level. Right. As I told you before, delta O greater means there is a presence of strong ligand. Correct. If there is a strong ligand comes, the d orbital splitted into two set with a greater energy difference. Delta O greater. So here delta O lesser, which means they indirectly giving you the idea there is a weak ligand. Careful all of you. There is a weak ligand. Okay. Delta O lesser mean there is a weak ligand. Clear? Now you go to the answer. So D4 system, this is the one we have, 4 electron. Anything happen to this 4 electron? Will they undergo pairing? No, because there is a weak ligand. If there is a strong ligand, these electrons undergo pairing. So let me discuss both condition. Okay, this is the D4 system. When delta O less than P, let me consider when delta O greater than P. Dear student, delta O greater means T2G and EG far away. It is happen only when there is a strong ligand. So delta O greater than pairing energy indirectly meaning there is a strong ligand. Okay. If there is a weak ligand, dear all, if there is a weak ligand, no pairing happen. So take the system as it is. So total there are 4 electrons. 1, 2, 3, 4. Right. And you know the d orbital splitted into which all level? First 3 orbitals you can place it below, that is called T2G. The last 2 orbital up, that is called EG in octahedral complex. First 3 orbital, it's having 3 electron, and last 2 orbital only 1 electron. So how many electron in T2G? T2G contain 3 electron, EG contain just 1 electron. That is the configuration. How many electron in T2G and EG? That's it. T2G 3, EG 1. The same system, D4 system, and it with a strong ligand. What happened here all of you? If there is a strong ligand, these 4 electrons undergo pairing. So these 2 electrons get paired. These 2 electrons get paired. This is the situation. And they will split it into T2G below 2 level 3 orbital T2G, and here we have EG. Dear all, T2G is the first 3 orbital. First 3 orbital, the electron is like this, and no electron in EG. So what is that? T2G contain total 4 electron, EG contain 0 electron. T2G 4, EG 0. So this is the main point here. Delta O lesser means they are giving the idea. Delta O lesser mean there is a strong ligand. Delta O greater mean there is, Delta O lesser mean weak ligand. Delta O greater mean there is a strong ligand. Alright. Next one. Out of NH3 and CO, you know NH3 is called amine, right? NH3 is called amine. And CO is called which one? Carbonyl ligand, right? Carbonyl ligand. Which will form more stable complex with a transition metal, and why? Dear student, amine is a monodentate ligand. Even CO, carbonyl, is also a monodentate ligand. And anything is special? There is no chelating power is not possible, right? Because both are monodentate. We may study that a special system is called metal carbonyls. Metal carbonyls. What is meant by metal carbonyl? The metal make a bond with the or the complex with the carbonyl, CO as a ligand. Metal carbonyl, you have studied metal and carbonyl ligand. When you consider, there is a chance to make a pi bond, right? Metal and carbonyl ligand, when you consider, carbonyl ligand have an ability to make a pi bond with a metal atom. You know, pi bond, one is sigma bond, one is pi bond. Normally, a monodentate ligand should make only one sigma bond, but CO, if it coming as a ligand, it have an ability to make a pi bond with the or double bond with the metal atom. You know, in a double bond, one sigma is there, one pi bond is there. All of you, please study how the sigma bond and pi bonds are forming. You may study sigma bond is formed by the overlap between the vacant d orbital of the metal atom with the lone pair of the ligand. And the pi bond is formed by the filled orbital of the metal atom with the vacant anti-bonding pi star orbital of the ligand CO. It's very careful to know the sentence. Okay. So metal carbonyl have an ability to make a pi bond, and you know that what is an extra bond is called synergic bond. Synergic bond is a self-strengthening bond. So when metal make a bond with the carbonyl as a ligand, the strong bond will be very strong because of the extra generation of pi bond. Okay, and this is pi bond is called what? The extra bond is called what? Synergic bond or self-strengthening bond. So the answer we can say carbonyl ligand, metal with the carbonyl is a more stable compound because they have an ability to make a pi bond with the metal atom. By the way, the bond or the stability get stronger. The bond is called synergic bond. Okay, the one. Identify the primary and secondary valency for the complex. The complex is given here, CO, cobalt, and there is 5 amine. Okay, NH3 5 times, and you have NO2, all right, NO2, the overall charge is 2 plus, overall charge is 2 plus, all right. This is the complex given, right? Identify the primary and secondary valency. In which theory you studied about primary and secondary valency? We have studied one of the theory called Werner's theory, right? What it is called? Werner's theory. According to Werner's theory, a central metal atom in a complex having two type of valency. One is called primary valency, the other one is called secondary valency. What is primary valency is also known as, dear all of you, primary valency is also known as what? Ionizable valency, whereas secondary valency is called what? Non-ionizable valency. Okay, careful all of you. Primary valency is also known as what? Ionizable valency. Secondary valency also known as what? Non-ionizable valency. And one more thing. What is the idea given by primary valency? Primary valency is nothing but the oxidation state. The oxidation state of the metal atom. Whereas secondary valency represent the coordination number. Coordination number for the complex. Okay, according to Werner's theory, every central metal atom in a complex exhibit two type of valency, primary and secondary. Primary valency is also known as ionizable valency. Secondary is called non-ionizable valency. Primary valency gives the idea about the oxidation number of the or state of the metal atom, and secondary valency is the coordination number. Let's calculate primary valency, that is our oxidation state. What is oxidation state of the metal atom in the complex, dear all? Cobalt oxidation state X, we don't know. NH3 is a neutral ligand, 0. NO2 charge is -1. Overall charge of the complex is +2. So what is X is equal to? +3. Correct. So primary valency is +3. What is secondary valency? Coordination number. What is mean by coordination number? We discussed before. Coordination number mean how many sigma bonds are created by the ligand with the metal atom. See, here the metal atom is cobalt. It is surrounded by 5 NH3, right? 5 NH3 ligands are there. And we have one NO2. You know, NO2 means nitrito N, right? NO2, nitrito N. all are monodentate ligand, right? All are monodentate ligand. So one ammonia, amine can make one sigma bond. All are coordinated bond, sigma bond. NO2 also one sigma bond. So total how many sigma bonds are there around the central atom cobalt? 6 are there, right? So number of sigma bond around the central metal atom which is created by the ligand is known as what? Coordination number. So coordination number is equal to 6. So primary valency is +3 and secondary valency is +6. Hope you clear Werner's theory. So dear all, from the chapter coordination compound, you have to mainly focus on this area. First one, the IUPAC nomenclature. Name to structure, structure to name, how to calculate the oxidation state, what is the charges of ligand, how to calculate the coordination number, and all the important theory which all the Werner's theory, Weibe theory, crystal field theory, and the special case what are metal carbonyls, and also the stability. You studied that stability of a complex is calculated by the checking the stability constant like that. So those all areas are important for the upcoming examination from the chapter coordination compounds. Hope you clear all the questions which we discussed here. So keep practicing all of you. Thank you all. Bye.
Brilliant Qatar, your trusted coaching partner for IIT, JEE, NEET, Science and Commerce tuitions with 10 years of excellence in quality training. Brilliant Qatar.